Good afternoon everyone. Hope all of you are fine. Welcome to Saurav sir's classes. Now today, before starting the lesson, I wanted to tell you about a riddle. So what is the riddle? The riddle says that you have 9 grids like this. There are 9 grids, 1, 2, 3, 4, 5, 6, 7, 8, 9. So name the endmost corner of the grid 0, 0. So this is the endmost corner of the grid, that is 0, 0. Just imagine it like the Cartesian coordinate system. This is the origin 0, 0, and this is a point Mn where both m and n are integers. Now each of the side length of the small squares is 1 unit. So 1 unit by 1 unit, this is a square. So now my question is, in how many ways can you go from 0, 0 to n, provided that you are only allowed these paths, the paths that are marked with the arrows. You cannot go diagonally through a square, or you cannot go inside the square. You have to only follow these border lines. So the question is, in how many ways can you go from 0, 0 to n? So what do you think, students? In how many ways can we do this? Okay, I will not reveal the answer to you now, but I am sure by the end of this course, of this class, you will be able to solve this riddle by yourself. So please look at it and give it a try. So today's class is all about a very interesting aspect of algebra that is known as the binomial theorem. The binomial theorem was invented long ago in the 1640s by two famous mathematicians named Isaac Newton, you all have heard of it, and Blaise Pascal. So Isaac Newton was very much more famous than Blaise Pascal. This is because Blaise Pascal has a lot of mathematical identities, but you haven't learned it up till now. You will learn it later, that in water pressure there is a thing called Pascal's law, and Newton is everywhere. So what is exactly this thing of binomial theorem? That's what we want to deal with today. So before getting into the binomial theorem, let's do an anatomical surgery of the word binomial. So what does the word binomial mean? Bi and nomial. So the word binomial comes from these two words, bi and nomial. Here bi means 2. And nomial means number of terms. So here bi means 2 and nomial means the number of terms. Then what is the binomial theorem? Exactly. If anyone can tell the norm that any algebraic expression which contains exactly 2 terms is known as a binomial theorem, is known as a binomial expression. So what we have learned, any algebraic expression that has exactly 2 terms is a binomial expression and binomial algebraic expression. So let's give a few examples of the binomial expression. So for example, x plus y is a binomial expression. A plus b is a binomial expression because it contains 2 terms. 1 plus 5x is a binomial expression because again it contains 2 terms. But notice that x plus y plus z is not a binomial expression. So x plus y plus z is not a binomial expression. So anything which contains 2 terms can be regarded as a binomial expression. Now a natural question might come to your mind. What about constant? Suppose I take a real constant. Can I say that is a binomial expression? So you can always argue with me. Let's say I take for example 5, and 5 you can write it as 4 plus 1. So you can say that 5 is a binomial expression. No, 5 is not a binomial expression. So let me tell you why. So in the beginning, binomial expressions and binomial algebraic expressions were basically used for algebraic purposes. So 5 equals to 4 plus 1 is a constant, but we cannot write x plus y as a single term. we cannot simplify this thing in a simple term. Neither we can simplify a plus b in form of a simple term. So, if the thing can be simplified to form a single term, so we will see every expression after its simplification. Like for example, x plus 2x plus y square. This is indeed a binomial expression. This is because it becomes 3x plus y square, which contains two terms. So binomial expression can be decided to be a binomial expression only after simplification in a stage where you cannot simplify further. So 5 cannot be regarded as a binomial expression. In fact, no constant can be regarded as a binomial expression. In fact, you can say that 2x, x also cannot be regarded as binomial expression. So the new definition of binomial expression, as per our understanding, goes in two parts. What? So all the terms must be simplified so that the resulting expression cannot be simplified again, and that resulting expression must contain two terms. So in that case, we call it a binomial expression. So we are done with binomial expression. Now what happens when we multiply a binomial expression by another binomial expression? Something might happen. Let's see. We will use the usual rules of algebraic multiplication and try to see what happens when I multiply binomial expressions. So what do I get? See, I multiply a binomial expression x plus y with another binomial expression a plus b. Okay, so I can write it as ax plus bx plus ay plus by. So binomial expressions is the general procedure to add to multiply two binomial expressions is like this. As you all know that this thing satisfies the usual rules of multiplication, and so we know now how to multiply two binomial expressions. Now let's get to a very interesting fact. What if I multiply a same binomial with another binomial? I mean a binomial squared. So let's see. We will now explore the powers of binomial expression. So since we are exploring power of the binomial expression, so let's just try to experiment with the thoughts that we have in our mind. So what do you think is a plus b to the power of 0, where a plus b not equals to 0? So is it 1? It's 1. We know that anything to the power 0 is 1, except I have mentioned the condition that this is a very important condition because 0 power 0 is not defined. So we must always check that this binomial that is inside, or anything that is inside with exponent 0, that this thing must not be 0. Or if it is 0, if the binomial results to form a 0, then the power must not be 0. Because as I have said that 0 power 0 is undefined, a very important concept that needs to be developed. So let's get back to our main topic. So a plus b to the power 0 is 1. Now what if I do a plus b the whole squared? So what means that a squared? What does it mean to square a number? It means that I multiply a number 2 times. So let's see. A plus b into a plus b. So as you know, it's just the standard thing. A squared plus 2ab plus b squared. Observe that when the power is 2, I denote the power by p. So when the power is 2, the number of terms is 3. See, a plus b the whole square, so the power is 2. The number of terms a square plus 2ab plus b square, then the number of terms is 3. Isn't it amazing? So here are only 3 terms, so everyone is able to memorize that or remember that or apply in their formulas. Now what happens that if I erase the power a bit? So let's just not raise it by a very large quantity. So I'll raise it just by 1. Say a plus b to the power cube. So a plus b whole cube is, as you all know, again a plus b into a plus b into a plus b, which is nothing but a plus b the whole squared into a plus b. So a plus b the whole squared, we have already derived what is a plus b the whole squared. So a squared plus 2ab plus b squared into a plus b, and hence what we get is a cube plus 3a square b plus 3ab squared plus b cubed. So again I observe that a plus b to the power cubed is given by this expression, and again the interesting fact is what we are again observing, that if the power is 3, then what is the number of terms? The number of terms is 1, 2, 3 and 4. So when I raise a third power binomial expression, so the number of terms becomes 4. So isn't it amazing? So what is the general property that you can assume? Now suppose I replace this 3 by any n. So what is the general property that you can assume? Exactly. The general property that we can assume is if the power is n, then the number of terms is n plus 1. Remember this is a very important concept in solving binomial problems, that if power is n, then number of terms is n plus 1. Very important. So I request everyone to please remember it thoroughly. This is because this happens to be one of the most important facts. Again and again I am telling you that this happens to be one of the most important facts that helps a lot in problem solving. So we are done with a plus b the whole cube. Now what if I raise the power a bit more? Now when I raise the power a bit more, you will understand that we are facing problems in memorizing the terms. We are even facing problems in multiplication. So what if I raise the power that a plus b whole to the power 20, a plus b whole to the power 30, a plus b whole to the power 40. So these problems appeared in the 1640s, and the fact was that what is the general term or the general expression of a binomial, of any binomial that is raised to the power of n. This problem was independently solved by both of them, and that is known as the Pascal's proof there is there and the Newton's proof is there. So there we get, to avoid the complicacy, we get the theorem. But before getting directly into the theorem, I want everyone to observe a thing. Notice that a plus b to the power 0 is 1. Okay. A plus b to the power whole square. What? A square, so the coefficient is 1 again. So we are taking only the coefficients here. The coefficients here means the constant values that are attached to the or multiplied to the unknown expressions. So 1 and 1. That is a plus b whole to the power of 1. A plus b whole to the power of 0. So a plus b whole to the power of 0 is 1. A plus b whole to the power of 1 is a plus b. And if we take the coefficients of a plus b only, it is 1 and 1. Now a plus b the whole squared. So what is a plus b the whole squared? A plus b the whole squared is a squared plus 2ab plus b squared. So a squared plus 2ab plus b squared. So again if we take the coefficients in, I write it in this way, 1. So the coefficient of a is 1. The coefficient of ab is 2. And the coefficient of b squared is 1. Okay. So what if I do it again for a plus b the whole cubed? So this a plus b the whole cubed is, we all know, a cube plus 3a square b plus 3ab square plus b cube. So again if we extract the expressions and write the ones on the lateral side, so we get 1, the expression is 3 from here, so it's again 3 from here, and it's again 1. Now students, try to observe a very interesting property in this thing. So the first thing is 1, we all know it. The second thing is 1, 1. So again it's very trivial for us. Now in the third thing you can observe that 2 1s are always placed on the lateral side of this triangular shape, and the middle one is just the sum of the previous 2 terms. Isn't it amazing? Let's verify it for the next step. So in a plus b the whole cubed, we can see that 1s are placed on the lateral side as I have told in the observation, and this 3 is just the sum of this, and this is just the sum of this. Isn't it very amazing a property? Doesn't it make things very simpler? Because now we are very well equipped to calculate coefficients up to any terms. What we have to do? We just have to place the new term in the middle of this previous 2 terms of the previous power of the previous row of the triangle, and then I can just add them and put it. So just follow this pattern and guess what can be the coefficients of a plus b to the power 4? Of course, the coefficients of a plus b to the power 4 is 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and 1. We can extend it further. What are the coefficients of a plus b to the power 5? Try deriving by yourself. 1 on the lateral sides, 4 plus 1 is 5, 6 plus 4 is 10, 6 plus 4 again is 10, 4 plus 1 is 5 again. And the pattern is very clear to us by now. So this triangle goes on forever on how much power of n you want. So you can extend it to any number of n because the natural number set is infinite. And now what we can do is we can get a plus b power 6, a plus b whole power 7, the coefficients of it. And the fact is that this triangle is known as the Pascal's triangle. So what is this triangle known? This triangle is known as the Pascal's triangle. So this Pascal's triangle was invented independently by Blaise Pascal in the year of 1640. Blaise Pascal was a very famous physicist. You have heard of Pascal's law in pressure. So Pascal's triangle was first invented by Blaise Pascal. So what did Newton do later? So Newton just modeled this Pascal's triangle to serve as a proof for his binomial theorem. So now, since we have observed the pattern, since we know what powering of a binomial means, so we can safely now go to define what the binomial theorem actually states. So let's define. So the binomial theorem says that a plus b whole to the power of n is, notice that this symbol here that I have introduced is the summation symbol. I'll explain the properties of summation later. Summation k equals to 0 to n ck a power k b power n minus k. Okay. So this is the statement of the binomial theorem, a very simple statement, though might be tough looking. This is because I have not defined these terms. So this sum here is the summation. So this thing here is what I call a summation. So summation from 1, so what do we mean by the term summation to n? Summation n means 1 plus 2 plus 3 plus 4 up to n. So what does summation n means? 1 plus 2 plus 3 plus 4 up to n. So here it means that the k will start from 0, it will gradually increase by 1. So if it is not mentioned anything here, just take it to be increasing by 1. So k is increasing by 1, so it becomes 0, 1, 2, 3. So the resulting expression will look like this. This will become nc0, a power 0, b power n minus 0, plus nc1 a power 1 b power n minus 1 and so on it will go. So this is basically the summation symbol. Now what is meant by this symbol? This symbol is basically derived from combinatorics, permutations and combinations. So we will get into the details of the theory later. So nck here means, just remember, n factorial by k factorial into n minus k factorial, where if you are not already known to this symbol, then I'll say that a factorial is just 1 into 2 into 3 into 4 into dot 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 a. Now for this purpose, I am just letting this n to be a positive integer. So this n is to be a positive integer, and this a, all the factorial things are also positive integers. Now you might ask me that, aren't there negative factorials? Doesn't there exist a thing called minus 1 factorial? Doesn't there exist a thing called half factorial? Okay, my answer to this is of course they exist. Half factorial means factorial of any real number exists. You will be very amazed to know that pi factorial exists, half factorial exists, and even e to the power pi factorial exists. But that is not the work that we are doing now. So it's just out of the scope. When you will go into higher classes, when you will come into colleges and universities, you will study there is a thing called gamma function that basically generalizes the factorial concept into the whole numbers. So for now we will just let it to be the positive integers for simplicity, and later if we have time, so we can discuss the gamma functions. For anyone who are interested in gamma functions, they can feel free to open the internet and exploit it. And of course you won't be able to understand, just see it as a storybook, as a fun, just as we do. So this is the binomial expression. So is the binomial theorem correct? So you must say that of course it is correct, but let us just verify it whether it's correct or not. So just let's try it for power 2. So a plus b the whole squared is, let's say, 0 to 2, it's summation nck equals to 0 to 2 a power k b power n minus k. So we can just write that a power 0 b power 2 minus 0 into 2c0. Okay, so before everything you must remember that 0 factorial is 1 by definition. So 0 factorial is defined to be 1 by definition. So you might ask if there is any logic for it. I would say that there is no particular logic for it. This is just the definition of how 0 factorial is defined. So as I was saying that 0 factorial by definition is 1. So just as we are checking, so a plus b whole power 0 plus a power 1 into b power 2 minus 1 into 2c1 plus a power 2 b power 2 minus 2 into 2c2, and here the expression ends. So we have summed up till 2, so we will go up till the 2th step. So this expression, if you simplify, comes what? A power 0 is 1, so b squared plus 2c1 is 2, a power 1 into b power 1, 2 minus 1 is 1, so 2ab plus a squared. And we have seen that this thing is remarkably correct. So the binomial theorem is remarkably correct, though we haven't got to the entire proof. Remember that proving a particular case, it cannot be treated as a whole proof. So I have stated it for all positive integers n, and I am proving it just for a value 2. That doesn't at all mean that this thing holds for everyone. So this is how we should do it. Now there are certain binomial expressions in which these things can be applied. So how can we multiply those expressions? So we will get a trick to multiply those expressions. How? So you all know the trick, but just that you didn't observe. Just observe what I am doing. So if I multiply x plus y into z plus say a, so what I am doing, I am just taking x from this box. So these are two brackets, can be treated as two boxes. So I am just taking x from this box, z from this box. So I multiply it and form xz. So I am just taking x from this box again and a from this box. So xa. So you are observing that the fact is that I just take any one from one of the brackets or one of the boxes, just any one term of the binomial, and just multiply it with the other two terms of the other two brackets. Okay. Now, what if I extend this expression to a bit more? Okay. So what would I do that if this expression has a b plus c more in it? So this is a three product binomial expression. So we are getting a binomial expressions in three products. So what we will do? What we will do is, again we will follow the same procedure. We will take this x from this bracket. We will take this z from this bracket. And then we will multiply it by both. So what it becomes? xzb plus xzc. So this is a very good mental trick to multiply faster. So since I have taken z one time, so let me take a another time. So we take x from here and a from here. So what we get is xab plus xac. So the work of x is finished. Now what can I do? So what will I do? So I'll take y from here, since the work of x is finished from both the sides. So I'll get y from here. So y I take. So y once I take with z. So y once I take with z, I get yzb following the same rule, and yzc plus I take y from here along with a. So I get yab plus YAC. Okay, so YAB plus YAC, and I see that if any term is left out, so no term is left out. Okay, so no term is left out more in the expansion. So what I'll do is, so now you did observe that how fast I could multiply these things together. Now this pattern of multiplication is quite interesting. I'll just take one element from one of the brackets, then take another first element from another bracket, then another element, and from the last bracket I'll multiply it both sides. Okay. Now what if I use this simple multiplication trick to, and this counting, our famous the counting combinatorics part, to prove the binomial theorem? Can we do it? Let's check. So what I am actually about to calculate in the binomial theorem, the actual part of the binomial theorem rests in, say, I want to calculate a plus b to the power of n. Isn't it? So a plus b to the power of n, how can it be written? As I told, in the power forms, a plus b into a plus b into a plus b and dot a plus b. So this is the power term of the expression. So I have expanded it. Now what I will do is, I will use that same multiplication trick again. What was the multiplication trick? I take a from here, I take another a from here, I take another a from here, and I take all the a's up to the n minus 1. From the nth term I take a. So what I get is a to the power of n minus 1 into a plus a to the power of n minus 1 into b. So this is what I get. For the second term, what I do? Now I take the first from a and the second b. So I have taken a, all the a's. Now I take all the a's plus, except from the second last term, I take the b. Just as the process I have described. That you will go up till the n minus 2th term, check with the n minus 1th term, take the first term, when the first term is over, so the work of the first term is over, and then get the second term. So what did I get? So a n minus 2. So I get a n minus 2, and now from the second bracket it's to be picked up b. So b into a. This is because the last term from the first bracket is a, and a n minus 2 b into b. So I think now we have already observed the pattern that what is going on. Okay, so you can multiply, but let's get this in a bit of combinatorial way. What do we observe in a binomial theorem is that there are occurrences, there are powers. So what does the power means? Power means a multiple occurrence. A square is a into a, so it's occurring 2 times. So multiple occurrences is the power. So tell me that if I want to get the coefficient of a power n minus k into b power k. So I just want to get the coefficient of this term. Okay, so what should I do? I must take a from exactly n minus k brackets. I must pick up a from exactly n minus k brackets and must pick up b from exactly k brackets. Okay, now how can I get a from exactly n minus k brackets? We all know this, we have done this in counting, that how can I get a from exactly n minus k brackets? That is nck ways. So in nck ways, as we have learned in combinatories, that how many ways can we get? So how many ways can we get a power n minus k from n minus k brackets? In nck ways. And from nck, so you think why is not anything multiplied with b to the power k? This is because if n minus k brackets is taken, then automatically k brackets is left. And therefore, if we don't take more a's, then the only thing that we have to take is b. This is because there is only two choices, a or b. Now if the choice a is exhausted, then what more we are left with? B. And therefore it is n minus k. A power n minus k can be taken up from exactly n ck brackets. We have learned this in permutations and combinations. So since it is chosen in exactly n minus k bracket, so what can we write? Now we need to sum over this n minus k. N minus k must be 1, must be 2, must be 3, must be 4. How can we do it? We can do it in a very simple way, as I have taught, by adding the summation symbol starting from k equals to 0 to n. And this is a one-line proof of the binomial theorem. So I have proved such a large theorem in a very simple way. But I recommend you to please everyone remember this multiplication trick. Not only the binomial theorem, this multiplication trick will help you in later cases also. So it will be very bad to conclude this video without a sum, a small sum. So I'll take a very simple sum that came in a JEE screening test. So the sum says that, question, find the number of terms. So my pen is a bit faulty here, sorry. So find the number of terms in 1 plus 5x whole power 8. So it came as an IIT JEE screening. So in those days there had to be a screening exam. So this find the number of terms in 1 plus 5x plus 8. So I request the viewers to just pause the video and try this one a bit. But we can solve it very easily by mentally. How? As I have always told that the binomial theorem, that any binomial, in the binomial theorem or in any binomial powers, if the power is n, then the number of terms is n plus 1. So here the power is n equals to 8. So the number of terms is n plus 1, that is 8 plus 1 to the power of 9. So I recommend you to do more sums on binomial theorem, because doing more sums will help you a lot in understanding, getting a grasp of the concept. So what I have provided must be sufficient, is necessary and sufficient for you to understand and do problems of binomial theorem at an elementary level. So this is all for today. Thanks everyone. Stay tuned for the next video.